Here we're going to think about the Nash equilibrium. What's the process we're going to go through? Well, we've already found the agent's best response function, and we've spoken about the principal's profit maximization process, giving us their ISO cost curves when they're minimizing their costs. And so what we have to do now, we have to bring those two together. We have to find the ISO costs and the best response function and put them in the same figure. Okay, so let's look at what that looks like. So what do we know? We know the principal prefers steeper ISO cost rays. Okay, so they prefer arrays that are steeper, where they get more quality for a given price than a lower quality for a given price. Right? So we know that for the principal. Now the thing is that the principal is constrained by having to provide the agent with incentives to implement the level of quality that she wants. So the principal knows that she wants to minimize her costs, but she is constrained by having to pay the agent enough to get the quality she wants. That means that she's limited by the agent's incentive compatibility constraint or best response function. So the Q that she wants to motivate Armin to provide must lie on his best response function. Okay, so she's trying to think, okay, what is the Q that I want given the constraint of his best response function or his incentive compatibility constraint? Well, that's the thing that limits how low her costs will go. All right, the best response function or the incentive compatibility constraint limits how low her costs will go when she's thinking through her profit maximization or cost minimization process. Okay, so let's keep all that in mind. And now what we can do is we can pair the figures up. What we've done here is we have two dashed ISO cost rays. Right? The dashed ISO cost rays are ones that are not at the Nash equilibrium. But the Nash equilibrium ISO cost ray and the incentive compatibility constraint are shown in the figure. So what can we see here? Well, we can see the best response function, as previously, is the purple line. What we also have is the ISO cost curve, here labeled C2, which is the ray from the origin. And we see that the Nash equilibrium is the point at which the two are tangent. There we can see it at point N. Okay, so we've got point N where the ISO cost curve and the best response function are tangent in this interaction. And we say here that Patricia would prefer to be at C rather than D or N, but these points are not feasible for her. So think about this, right? If we look at the figure, point C is preferred to point N. All right, so what's happening at C? Basically, she can pay half the price for the same level of quality. She'd really like to be able to do that and be on a steeper ISO cost curve, but can she get there? No, she can't. She is constrained by the agent's incentive compatibility constraint. That limits what she's able to do. Right? It's kind of like a feasible frontier like you've seen previously. It's limiting what is feasible for her to choose. Similarly, if we're comparing points N and point D, well, we can see here, if she has the option, would she choose point D? No, she'd not choose point D. What she can do instead is she can in fact offer a higher price and get more quality and move up to point N. So we saw that C was infeasible relative to N, but D is not an optimum. It's not where she is minimizing her costs. She would not choose to operate at point D. Instead, she's going to increase the price that she provides and get higher quality and move to point N. And that's how we're going to be getting this Nash equilibrium. Now, the next thing though that we have to think about is that we know that the cost minimizing price will be somewhere on the incentive compatibility constraint, the ICC. Now the cost minimizing price will be determined by the following condition as a result. The slope of the ISO cost curve, or the ISO cost ray, is going to equal the slope of the agent's best response function. Now what that means is that Q over P equals Q sub P. Okay, so the ratio Q over P, the slope of the ISO cost ray, is equal to Q sub P, and that is the slope of the best response function. So slope of the ISO cost ray, Q over P, equals slope of the best response function, Q sub P. So what do we have to do to find Q sub P? We'd have to differentiate the best response function with respect to P, which is what the principle would do. And that was what would allow us to eventually find the Nash equilibrium combination of price and quality. Now, when we see this, slope of isocost ray equal to slope of best response function, that should immediately set off alarm bells. And those alarm bells should be telling us that, yes, we remember, this is the same marginal rate of substitution equals marginal rate of transformation rule that you've learned previously. The slope of the best response function is the negative of the marginal rate of transformation. The slope of the isocost ray is the negative of the marginal rate of substitution. So those two things are equal to each other, MRS equals MRT. That's the same thing we get when we have the two slopes being equal to each other. Okay, so it's that same MRS equals MRT rule, which is also what we get when the slopes are equal. So the slope of the isocost ray, the negative of that is going to be the marginal rate of substitution between quality and price. The slope of the best response function is going to be the negative of the marginal rate of transformation of paying a higher price into receiving a higher quality. So that's just a reminder of what we have there and this process that the principle has gone through in order to find the Nash equilibrium. So, what do we think about it? Well, having found that tangency point with MRS equal to MRT, we can see that we're going to have now a combination Pn Qn. So the Pn is going to be equal to 4u bar, and the Qn is going to be equal to 1/2. And the allocation Pn/Qn, putting it in order, sorry, the allocation Pn/Qn is a Nash equilibrium because it's a mutual best response. So why is it a mutual best response? Well, it's a mutual best response because Patricia's choice, given Armand's strategy choice determined by his best response function, is to choose her cost minimizing isocost ray. That's the one that's steepest given what's feasible for her to do. And for Armand, his choice, given Patricia's price offer, is the best that Armand can do. It lies on his best response function. And remember, at every point along his best response function, what is he doing? He is choosing the maximum from his value, right? He's optimizing at every single point on his best response function. So as a consequence, a point on his best response function has to be his best response to what the principle would offer him.